The next two lectures focus on changes. Changes observed in the atmosphere, the hydrological cycle, and ecosystems in this lecture. And the next lecture talks about changes observed in the ocean and the ice system, right? The cryosphere. All right, and we're talking about timescales of 100 years, okay, with a focus on the last decades, because there were the most dramatic changes ever recorded. Okay, in part A, we focus on the atmosphere and we look at changes of CO2 concentrations in the atmosphere. And I introduce you to the famous Keeling curve. And we look at surface temperature changes, okay, the global warming, the observed global warming. In the second part, okay, we look at changes in precipitation patterns, observed changes. Is there any indication, okay, that there's more rainfall in some regions and less rainfall in other regions? In the last part, I want to talk about ecosystems, changes in ecosystems, and it can't be linked directly to global warming, but it can be linked to population growth, and it's population growth-driven changes in ecosystems. And then I want to introduce you to linkages between ecosystem services and human well-being. And then we talk about major human impacts on ecosystem services and degradation of ecosystems. And indeed, that degradation is under immense stress because of global warming. Okay? All right, so let's talk first about the atmosphere, changes observed in the atmosphere. And the first thing we do is we talk about the carbon cycle. Okay, so the cycle of carbon within the climate system. Okay, that's what it is about. Okay, and you can look at diagrams like this. This is the carbon cycle. It's about the conversion or the transfer of carbon between different components of the climate system. And you find diagrams like this on the internet, and it captures the key aspects. Okay, you have CO2 in the atmosphere, and it's used for photosynthesis, both on land and in the ocean. Okay, that's the process that takes up CO2. Okay, but over land you have a respiration processes that releases the CO2 back into the atmosphere, and then over the oceans you have an outgassing process that releases CO2 back into the atmosphere. So you have these cycles. You have an ocean cycle, you have a cycle involving the vegetation, and indeed you have combustion of fuel. You have a flux of CO2 into the atmosphere because of humans. Okay, it's the combustion of fuels that adds CO2 of the atmosphere. So now you become more interested. You want to know the numbers. So how much, you can add numbers to the fluxes, and you also want to know how much CO2 is actually in the atmosphere, how much is in the ocean, and stuff like that. And that's what scientists have compiled over many, many years. They put numbers to these processes. And I'll show you one example. Okay, so we find diagrams such as this one here. Okay, in this diagram you can see that there's an atmosphere. It's this light blue box up here. There's the ocean as represented. Okay, well, we have the land and we have vegetation represented. Okay, volcanoes are here, fossil fuels here. So what's shown here is one part deals with reservoir sizes, the stock size, how much carbon is in a component. for example, an atmosphere, there's this black number, okay, which is 589, and this is an estimate, a reconstruction of how much carbon was in the atmosphere at just before 1750, before the Industrial Revolution started, essentially. And the units of these numbers are petagrams, and petagrams, 1 petagram is 10 to the power of 12 kilograms. It's equivalent to 10 to the power of 9 metric tons. These are huge numbers, but anyway, so this is the unit that we use to compare. Okay, and these black numbers here, and you can see how much the vegetation has, how much of the carbon is in the vegetation, how much is in the ocean. And in the ocean you find these huge numbers, 37,100. Here you can learn that the ocean holds most of the carbon, actually. Okay? All right. So that's one thing. Now the red numbers are actually the changes, and you can see that there's an increase in the atmosphere. This is since 1750, okay? So in due course of the Industrial Revolution, 240 plus minus 10 units of CO2 have ended up in the atmosphere. So this is the human contribution. Okay. So now what are all these errors? The errors are now estimates of individual fluxes. Okay, the fluxes. Like over the oceans, there's 60 units, and this is a flux per year. Okay, how many petagrams of carbon per year? It's a 60 goes into the ocean, and there's an outgassing, 60.7 here in this. You know, there's rivers and stuff, and you get all these errors, and you get estimates for photosynthesis, you get estimates for respiration, stuff like this. And the red numbers are now the changes. Okay, these are the changes caused by the disturbance of anthropogenic CO2 emissions. Okay, including land use change. Okay, land use change has become a source of CO2 for the atmosphere. And you can see that the flux change is 1.1 here, plus minus 0.8. And you can see the CO2 emissions as a flux in here. And you can see the fluxes that come from, you know, the outgassing, and I said that before, photosynthesis, all that stuff. Okay, and that gives you an idea of how complex the system is. And then you get a little bit confused and think, well, how can we actually now know what has changed? Okay, so what you actually need to do is, it's relatively simple. You just need to measure CO2 concentrations. Because the CO2 concentration itself is a measure of the entire system. Okay, so if you measure it in the atmosphere, you know how much it actually has changed over the years. And you can measure it in the ocean. You can see how much has it actually changed in the ocean. And from that, you can actually learn many, many important facts. For example, how much of the human-induced CO2 has ended up in the ocean. And we will talk about that later on. But let's talk about first about CO2 concentrations in the atmosphere, okay, as the result of this entire cycle, which is shown here. Okay, if there is not an equilibrium, the CO2 concentration changes in the atmosphere. And this brings us to the observed changes of CO2 and the so-called Keeling curve. It's a graph, and it's a famous graph. Okay, that it's a graph that represents the concentration of carbon dioxide in the Earth's atmosphere since 1958, measured at Mauna Loa Observatory of Hawaii. And the Keeling curve is named after its creator, Dr. Charles David Keeling. And here's a photo You know, that's Dr. Keeling. So Keeling began studying atmospheric carbon dioxide in 1956 by taking air samples and measuring the amount of CO2 they contained. Over time, he noticed a pattern. The air samples taken at night contained a higher concentration of CO2 compared to samples taken during the day. He drew on his understanding of photosynthesis and plant respiration to explain this observation. Plants take CO2 during the day to photosynthesize or make food for themselves, but at night they release CO2. And that was the starting point. And he continued to measure CO2, and that these measurements still exist. Okay, this is the longest CO2 record, the direct measurements of CO2 that we have. The Keeling curve, how does it look like? And here's the complete record of the Keeling curve. Okay, this is the Keeling curve. The x-axis is a time axis starting in around 1960, okay, until today, okay, until 2020, 2023, okay. And the vertical axis, the y-axis, is CO2 concentration in parts per million, and ranging here from 310 to 430. Okay, and you can see the curve, and the curve has some undulations, some changes happening here, some smaller changes, but overall there is this positive trend and increase. Okay, and it seems to be even increasing more towards later times in this series, time series. You can see an acceleration. Okay, so that's the famous curve. This is the link to the anthropogenic effect, the anthropogenic greenhouse gas emissions, and the link to the greenhouse effect and the global warming that we will be discussing later in this first part. And so what are these small variations? The small variations are shown here, blown up over a time series of 2 years, and you guessed it right, seasonal variation. It's a seasonal cycle. A seasonal cycle of enhanced photosynthesis, yeah, or enhanced respiration. So you get a seasonal cycle. You know, it's a relatively small magnitude. You can estimate that here it's something about 10 parts per million is the change that you get. Okay? Wow. Okay. So what you also can do is you can make a connection between the Keeling curve and paleoclimate data, observations, reconstructions of CO2 from ice cores. Let's have a look how that looks like. So the Keeling curve. Okay? Just have a look at the last 300 years, and the 300 years. If you look at the last 300 years, you see it's relatively stable CO2 concentrations at around, 275 or so, relatively stable, and then around start of the 19th century, and then you get that increase, and then you get a sharp increase towards the end, and exceeding 400, okay, parts per million. Okay, you can bring it even into the longer term context of the past 800,000 years, okay, from ice cores. And here you can see the ice age cycles. You can see CO2 variations never exceeding 300 parts per million. And now we are in a CO2 regime where we are above 400, way above what we had over the past 800,000 years. Okay, and that's, you can bring it into context with past climate conditions. Okay? This is what we call the Keeling curve, a very, very famous curve. All right, so let's have a look at surface temperature, global warming. Okay, and I want to show you. This is a curve, an average temperature, measured from 1860 to 2021. Okay, and I want to show you some videos, animations afterwards to illustrate different aspects. So this is just time series, and you can see that there is a sharp increase since the 1980s. You can see that significant increase of temperatures. Since 1980, we're talking about 1 degree increase in global temperatures. Okay. And we talked about other aspects of that we had periods of global warming slowdowns, and we have periods of accelerations. Okay. All right, let's have a look at some videos if they move. Let's see. So what's shown here is the globe, the distribution of temperature anomalies. And you can see regions that are blue and regions that are red. Okay, and the range is from -2 to +2 degrees Celsius. And red corresponds to warm and blue to cold. Okay, and when this time series starts, it starts at 1880, 1884, some reconstruction, and then we go into the era of observations, with the most detailed information since satellites were discovered. Okay. And I'd start this. Let's have a look. There's not much happening here. Initially, a little bit you can see. But have a look how the color changes. We're now 1950. We're going to 1960. We're coming to 1980. No, 90. And we are coming into 2022. And this is how it looks at the moment in terms of temperature anomalies. And what you can see in this graph is that you get the biggest warming effect in the northern hemisphere, in the polar, subpolar regions, and extending over Europe. You can see in northern Asia as well. Okay, so you get the least impact near the equator, in particular over the ocean here. And you can see that there's some mixed signals over Antarctica. You can see some with a warming, some with a cooling. Okay. So let's have a look at the same data, but as a different type of animation. And let me just go to the next slide. No, this is not the next slide. Next slide. Go here. And that's a different way to present the data. Okay, and what's done here is that the Earth is subdivided into different segments. You start at the equator, and then you essentially cut into different segments. We're talking essentially about the tropics, subtropics, mid-latitude, subpolar and polar regions. And we give it a color code again, and the color code is blue is, minimum -2 degrees Celsius change, and red is a +2 degrees change. Okay, now you can look at the movie and you see these markers swing over, and you can see actually variations. Sometimes negative. There's something we call interannual climate variability, and you learned about that. In particular, for the north polar regions, you see that there is a swinging back and forth. This is something that we call the Arctic oscillation. Okay, there's also something. So don't be confused that you get so much variation. Let's have a look at this movie. Okay, we are starting about now. We're reaching the 1900s, And have a look. You have a look at at the sliders. Yeah, you can have a look at the sliders. 1930. We come to 19. And you can see sometimes the Antarctic polar regions are opposite to the northern hemisphere polar regions, which is an interesting feature. See how complex that is. But now we're getting into the warming phase. 1990. We go to 2000 and look at the Arctic slider, how it goes into extreme high temperature range. Okay, and this is how it looks like in 2021. So with this, if you look at movies like this is again from the NASA Scientific Visualization Studio, you get actually feeling for the global the trend, the warming trend, and these oscillations that we have on Earth, the interannual variability. And I have another video representation of this feature. So let's see whether I managed to do this. Next, it's something that's known as the climate spiral, a very famous spiral. Okay. So what's done here in this simulation is it shows the temperature anomalies in a diagram which actually runs around these circles. So imagine that you have no change, and as no change in January would be here where my mouse finger is now, and no change in February would be the green curve along here. So you go along the month of the year around, and if you had no changes, you would get a circle which always stays on that green circle. Okay, but if you get changes, this entire thing turns into a spiral. Okay, and we have a look at this, how it looks like this spiral. Okay, so you can see the year in the center of this graph. So we're reaching the start of the 20th century. Okay, we're getting 1920. All right, let's see. All right, 1940. There was a little bit warming phase there. But let's see what happens once we go into the last 30, 40 years. Again, that's why it's called the climate spiral. It's all happening, start to happening now. Okay, you can see the warming effect. And you can see that it's in all seasons. That's why these graphs are so excellent. You can see all seasons, and and you get this spiral effect. And then you can turn it around, and you can put some axis to it, and you can see that you get that global warming signal. All right, so it's just a few more things. I don't want to show this again. Okay, it's about the attribution, and we will talk about the attribution in more detail in some of the future lectures when we talk about the IPCC. But just here as a quick link, the observed warming that we experience is shown in this graph on the left. We're talking about more than 1 degree. And we also can attribute the causes to this warming. Okay? And it's shown here on the second one. This is sort of the aggregated contribution of the warming. Okay? Assessed from attribution studies. Okay? So the total human influence, and we have the well-mixed greenhouse gases, which even overshoot the warming signal, but which are balanced by other human drivers. And we're talking more about the aerosol effects. Okay, and this can be split up into individual components. You can see some that are in red, which contributed, which drove the warming, okay? And some in blue, which actually counteract the warming. And you can see that carbon dioxide plays the biggest role, methane. That's the biggest drivers. Okay. And sulfur dioxide is one of the, essentially linked to aerosols is one of the biggest players counteracting the global warming. Okay, but overall, the global warming that you get is approximately what you get from CO2 alone if you just ignored all other features. And that's why CO2 is such a standout, a variable feature that we always look at CO2, because it sort of represents a direct measure of the warming effect that we have. So humans are responsible, greenhouse gas emissions masked by aerosol effects. That's what we have. And the last little link here is, and I showed these images before, indeed we have also changes of temperature extremes also observed all over the world. Okay, we're talking about heat waves here. Okay, and this is a little sketch that I showed before. It's a time series from one decade to the next, and number of heat wave or extreme temperature events, okay, observed per year, and now distributed to different regions, different continents: Africa, Asia, America, Europe, and you can see this increasing trend of extreme temperatures. So, and this concludes the first part of this lecture.